morning, ladies and gentlemen. This is about strategies for using BIM in assessment and monitoring of large steel structure. It's an application to the sport hall here in Guimarães, Portugal. It's the introduction. Nowadays, steel structure have an important role, especially for large-scale structure, warehouses, hangars, industrial structure. Of course, monitoring the health of that structure is crucial because of their failure can lead to catastrophic safety breach and economical impact. Of course, the whole things about BIM and how BIM can manage the data from the structural health monitoring system. The objective of this study is intended to develop methodology that support the assessment and monitoring of the steel structure. The main objective that we will go through is explore the structural health monitoring practices nowadays, the role of BIM, how it will manage and elevating the process of SHM, and the result, we will go through the guideline to develop a plan for that particular case in our study. Our research case study, it's a sport hall called Montuoso de Guimarães. It's near the campus. It's just, I think, 10 or 15 minutes walk. The initiation of the study that the administration of the sport hall, they are willing to upgrade the whole roof to be adequate and to be enough to withstand the new audio and video equipment to help more develop or more sophisticated concerts and fairs. Of course, for this study, we will develop a BIM model. We will go through the safety verification by finite element. We will develop also the load test plan, actual load test plan to the frame. And lastly, we will provide a guideline to develop the safety, structural safety plan. Something just like to get through the idea about lecturer review for this thesis. What is structural health plan? It's the assessment, the condition of structure, and detect any changes or damages that affect its intended use. Of course, this can be due to the time that affect the performance or any change in the purposes and that the intended building have been developed before. Just like in our case, it's just a sport hall. Now it developed to hold more concert and more fairs there. It's basic thing. It's just like human body. We have sensor, nerve system, and the human body that will manage the data and give us the warning. There are two main methodology or techniques that manage the database, that manage the structural health monitoring methodology, model-based and database. And nowadays there is a hybrid technique that can fill the gaps between these two main branch techniques. The model-based is mainly we need to develop a model for the physical structure, either a finite element in our case or module model, which is deal with vibration of the building, or database, which is actually it will compare the data with damaged part with undamaged part, and any deviation between the undamaged part, it will be considered a damage or developing to damage. Also, the structural health monitoring system consists of main two parts. The sensor that will collect the data from the environment, and the other big part, which is processing the signal that we got from the sensor. It's going through many iterations to get the final warning system in the structural health monitoring. Also, we are dealing now with BIM, so we are concentrating on the seventh dimension of BIM, which is facility management, because we are supporting maintenance and operation and monitoring by linking data to the model. Basically, the integration between these two methodology can be effective for data management that obtained from the sensor and merge that information with the model itself. It can give us more effective design and planning for the structural health monitoring system, create a unique digital model that includes the sensor data that we collected, better management, interpretation, and analysis of measured data. And the last one is the most important, better and fast emergency response. The guideline to set up the design structural health monitoring plan. We need to go with that one. It's model-based or database system. It's should we develop a model by finite element or module model, or only collecting the data and compare it between damaged part or undamaged part? What type of data that we need to monitor? We have strain data, we have displacement, we have force, we have rotation, we have vibration. Also, should it be a short-term observation or long-term observation? Because also it depends how you will manage that big amount of data that you will collected for a long period of time or a short period of time. You will manage a locally or on a global scale of the whole structure. Also, you will manage or you will monitor a static monitoring load or dynamic monitoring load. Here, I have been developed a simple schema that we can get an idea what we will manage. But before that, we have been selected to monitor the building or structure on long-term observation. It will be continuous tracking of static load, which is mainly due to the new load requirement for audio and video equipment. We will measure strain because due to the characteristic of the building, it's hard to measure other things like deflection, which is what we have been did and later on in load test plan. And of course, we will generate a model, a finite element model for verification and find the sweet spot between the load that we will apply. And we will, of course, we develop a Revit model that will be later on be used as a structural health monitoring warning system. We have here initial Revit model. Of course, it contains structural geometry, structural analysis, model property, sensor virtualization. We have the philosophy that we have been discussed about the structural health monitoring, about the type of sensor, what type of structural element that we will manage. It's global or local, connection type. Here, our parameter. After that, from Revit model, we will get finite element model, axial forces that we have. We will have also sensor location, deflection. During the process type, process from that, what we have from the information, we will develop the sensor family that will include it or will be attached to the Revit member. Data defined sensor group location. Also, from structural health monitoring, we will also develop cloud-based information because we will use wireless connection, and of course, by Dynamo, we can manage the data to integrate that one with the interactive Revit model. This is our model. I had used Revit 2024. We have been selected. because, of course, it's easy integration with the robot structure analysis for finite element, and of course using Dynamo later on for data interpretation between the interference. Uh, what I have the methodology with that I will model a Revit model. Of course, I will generate a Revit model. After that, I will transfer it as an analytical model using uh, analytical automation feature in Revit 2024. This is a new one. I think it's have been started with 2022 or 23. So I say this is a good way to put it in practice. So we have on the left the Revit model, and after the automation, I have this ABC noded that I have. Of course, this is applied to the whole model, but this is for demonstration the difficulty that I have here. These are A and B and C and Revit model. When I did automation, I found this noded, that it should not be just like that. It should be connected with each other to make the structure work as intended. Now, finite element or robot structure analysis will consider these are a separate elements. Also, I can see in B, which is also huge because it's composite section here in purple color. The Revit show is there are two different separate members. They are not connected with the post. So in this case, I went with the manual modeling of structural model using Revit, and I got everything set as intended, as structurally should be. After that, have been shifted the model to export the model to robot structure analysis. As we can see, this is, of course, this photo after, or this screenshot after a grouping. We intend to use the finite element for two reasons. First of all, for first one, to verification of safety of structural. After that, we calculate the deflection and compare it with the actual load test. Of course, there is many things need to be set before going with the verification. As job references, we need to use the European design code. Verification group also, which is very important because it depends mainly on slenderness and buckling length. The buckling length for each group have been defined by member definition. And also because there is some member, they are composite sections in the truss system. So these are the three main composite section. Of course, now we set everything. Now we are ready to start the verification. Of course, we need to switch windows and interference between the design and verification. The most important thing here, we need to, in configuration, in window number 3, we need to set the method to appendix B. And from here, we generate a verification report. As you can see, most of the members, they are satisfied. Only 2 members, we have a slightly more value than the European code. The limit is 210. We have now 218. Of course, we need to consider it as it is. Of course, the structure is there, it's stable, and we thought that this is okay to go with it. There is no need to refine more or change the load criteria. Of course, we did a load combination, so we set this load combination to the existing case. Of course, now we applied, go to the load case scenario. We applied the design, the load case scenario that we will that the structural will be suffered. We concentrated the forces or the scenario on the axis D, and here that we got the deformation in the members, as shown in the figure 19. Now we developed a load test plan, how we will manage the load test, the actual load test to the structure. We have 5 load point, the load ranging from 900 kilogram to 1,600 kilogram, only on the XSD, which is we thought that this is the truss that will suffer the most deformation or stress in that part of the structure. Also, we monitored the structure by 14 LVDT sensor that it will measure the deflection. And here you can see that this is the setup for the test. We have A, which is showing the LVT sensor. B, there are signal condition unit transfer from analog to digital. And this is actually what we have hanged from the truss D at axis D. We got series of data measured and recorded, and it's have been processed manually in this Excel sheet. By applying this information to the graph, we can see in graph A is vertical deflection for the load test. The maximum value that we reached is 7.3 or 7.2 millimeters. And comparing with the model, with the numerical model, at the node, the idea is this value at the node, we got 5.9 millimeters is the maximum deflection for the node. By this, we can see that there is 20% result from load tests more than the numerical model. And the pattern of the deflection, they are almost match at the shape of the deflection. For developing the structural health monitoring plan, comparing the structural model with getting the data from the structural model, we proposed 8 sensor group and the location that's most critical. Also, we suggest to use FBG sensor gauge sensors that we will use for monitoring the strain values. And also for wireless connection between sensors, we select this flow chart, which can be read as sensor send signal to the main computer on the site. It's Raspberry. And after that, by using middleware, can send the data to the cloud database, and from cloud, by using Dynamo, it can transfer or translate that data to a virtual representation. Of course, we need to develop a family. It's additive component in Revit family to reflect that information. It contains the sensor ID, the member that will attach, the sensor will be attached to, and of course define the limits of strain value, the maximum and minimum. That it will lead the sensor will change the color in case exceeding the limits. Of course, we developed that also from the finite element from robot. And at the end, we develop a Dynamo script. Of course, I didn't put here any references that will generate the signal that trigger the sensor coloring onto the model. This is, I think, that we go through all. So the conclusion that the structure is safe. The management of the sport hall can load the new equipment safely. And also we developed a guideline for structural health monitoring plan. And I think this is all. Thank you for your attention.